Hi everyone. So in today's video, we're going to be doing some more practice with simplifying trigonometric expressions using the identities that we learned in yesterday's video. I wanted to start by just reminding you about what are the trigonometric identities that we talked about last time. And then we'll get into, this video will mostly just be a bunch of examples of slightly more complicated expressions and some sort of like strategies for simplifying them. Okay, so the two types of identities we talked about last time were, we talked about basically, I never really know like a great name to give these, but it's basically just writing everything in terms of sine and cosine. So every trig function can be written in terms of sine and cosine. So you can think of sine and cosine as like the building blocks. So that includes tangent of theta can be written as sine of theta over cosine of theta. Cotangent, which is the reciprocal of tangent, can be written as now the reciprocal of that, so that's cosine of theta over sine of theta. And then cosecant, so that's the reciprocal of sine, so that can be written as 1 over sine of theta. Oops. And then the last one would be secant, and so that's the reciprocal of cosine, so that can be written as 1 over cosine. So one strategy that we saw, and we're going to be doing a lot of this in today's examples as well, is taking whatever functions or whichever trig functions are involved in your expression and rewriting them to be in terms of sine and cosine, because that will allow you to kind of see what can be combined or canceled out in different ways. So the other types that we talked about were what are called the Pythagorean identities. So the most important one to know is cosine squared of theta plus sine squared of theta is equal to 1. So that just comes from the unit circle equation and the fact that cosine and sine are the x and y coordinates on the unit circle. So if you remember that one, to find the other two, all you have to do is divide everything by the same thing. So for example, if we go through and divide everything in this equation by sine squared of theta, then we'll get cotangent squared of theta plus 1 is equal to cosecant squared of theta. And then if we start again with that original equation and instead we divide everything by cosine squared of theta, then we get 1 plus tangent squared of theta is equal to secant squared of theta. And then from these ones, you can also rearrange them, right? So we saw, and we'll see some more, I believe, examples like this today where, for example, if you have an equation or an expression that involves like 1 minus sine squared of theta, well, that's the same thing as cosine squared of theta, right? Because if you were to subtract sine squared of theta from both sides, you would get cosine squared of theta is equal to 1 minus sine squared of theta. So the general strategy was when you see some of these different trig functions being squared and you suspect that, maybe there's an identity you can use, look at the identities and see how you can rearrange them to suit the needs of that specific question. So we'll add one more type of identity to this list at the end, but first I want to focus again on just using these ones a little bit more. So we're going to have like two new strategies basically. So two strategies for simplifying trigonometric expressions. So in the examples that we did in the last video, we started with some examples that were pretty simple, where really all you had to do was rewrite things in terms of sine and cosine and then just kind of see what cancels out. And then we also did some examples that were like pretty straightforward, just applying the Pythagorean identities. The ones that we're going to be looking at now are going to be generally like either multiple fractions that need to be combined or a fraction that has different parts to it. And so there's going to be two main things we're going to be doing. So the first one that we're actually not going to, this is probably the less important of the two, but I just want to cover it quickly first, is something we talked about yesterday, which is splitting up a fraction using the fact that if you have a plus b over c, that's the same thing as a over c plus b over c. So we'll see that. We'll do an example in a second where this is how we'll do it. We'll take a fraction, kind of split it apart, and then from there, there's other things we have to use. Well, then we'll look for, okay, is there a way, can we rewrite everything in terms of sine and cosine? Can we use other trig identities and kind of take it from there? So an example that would be a good one to use this method would be if you were supposed to simplify cosecant of t minus sine of t divided by cosecant of t. So why is this one a good candidate for this approach? Well, first of all, I mean, it kind of looks like this, right? You have a fraction that can be split apart. But we'll see some more examples later today that actually will be a little bit where there's an easier way to do them, where doing it this way would take longer. The reason that in this case it's a good way to do it is because you can easily see that if you were to split this up, you would have cosecant of t over cosecant of t, right? Which is 1. So if you can see something obvious like that, where like you can definitely tell it's going to simplify if you split it up, then that's kind of a good hint for you that you should use this method. So if we split this into two fractions, so the first one, as we just mentioned, is just going to become 1. And then the second one, we want to rewrite this, the second fraction here, we want to rewrite this, the denominator, in terms of sine and cosine to kind of see how we can simplify it. So the first fraction is just 1, and then the second one we can write as sine of t over 1 over sine of t, right? Because cosecant is the reciprocal of sine. And then, so sine of t divided by 1 over sine of t, that's the same thing as doing sine of t times sine of t over 1. Right? So dividing by a number by a fraction is the same as multiplying by the reciprocal of that fraction. So we're left with 1 minus sine of t times sine of t, which gives us sine squared of t. So if we go back to those Pythagorean identities, so these ones here, if we were to take this one, and actually I already mentioned this earlier, if we did 1 minus sine squared of t, in this case, we would be left with cosine squared of t. So we're just using kind of a rearranged version of that identity to conclude that this is cosine squared of t. All right. So let's see another method, and then really the rest of them that we're going to do, we're going to use this kind of other method. And I'll kind of point out in which example, like in some examples, there will be more than one way to do it. And that's often going to be the case with these questions. There will often be kind of more than one way to get started. And I'll try to tell you what I think is the easiest way, but usually it's not too different. You know, as long as whatever you're doing is valid mathematically, you should be okay. Okay, so second method we're going to use is we're going to start by writing everything in terms of sine and cosine, which, you know, that's a strategy we already talked about last time. But what's new here is that we're going to, using the fact that we're rewriting things in terms of sine and cosine, that means that you'll have some fractions, right? So going back to our list here, if you have anything that isn't just sine or cosine, it's going to be a fraction. And so you'll basically be introducing fractions into your expression. And by introducing fractions, that will give you the opportunity to make common denominators. So that's really the key part of this method. And so this is going to be, some of these are going to actually look kind of complicated while we're in the middle of doing them. And you just kind of have to trust that they will get simpler. A lot of these you'll kind of feel like you're doing something wrong at first because it'll feel like it's getting more complicated. Okay, so let's look at an example here. So this is an example where if you wanted to, you could actually use method 1 on this. So you could start by breaking this up into 2 fractions and then simplifying each of them. But personally, I think that the method we're about to use is a little better on this specific example. But I would encourage you to try it the other way and kind of verify that you get the same answer either way. Okay, so we're going to rewrite this as, so let me just rewrite it down here, secant of theta minus cosine of theta over sine of theta. So really the only thing that can be written any differently is we can rewrite secant of theta as 1 over cosine of theta. Okay, so you might look at this and say, like, common denominator where? Like, there's really only one fraction. And so that's what I meant when I said we're going to kind of look like we're making things more complicated. So we're going to make a common denominator in the numerator. So what would the common denominator be between these two things? Well, it has to be cosine of theta. So to get that common denominator, we're going to multiply this second part by cosine of theta over cosine of theta. So we're kind of introducing something that will seem like it will make it more complicated, but eventually will actually lead us to a simpler answer. So by doing that, making that common denominator, we're now going to have 1 over cosine of theta minus cosine squared of theta over cosine of theta, all divided by sine of theta. So resist the urge to go in and simplify this, because if you simplify that, then you're basically just undoing what we did earlier by making the common denominator. So instead, what we want to do is put these two fractions together. So in the numerator, we'll now have 1 minus cosine squared of theta divided by cosine of theta divided by sine of theta. So now we want to think back to our Pythagorean identities. So whenever you see something involving a squared trigonometric function together with 1, it's usually a good idea to look at your Pythagorean identities. So we have a Pythagorean identity that tells us that because sine squared plus cosine squared is equal to 1, that means that 1 minus, writing this backwards, 1 minus cosine squared is equal to sine squared. So that comes from the fact that cosine squared plus sine squared is equal to 1, so 1 minus cosine squared is equal to sine squared. And so that allows us to rewrite this as sine squared of theta over cosine of theta over sine of theta. So now we want to again use that method of rewriting, instead of dividing, rewrite it as multiplying by the reciprocal. So we can rewrite this as sine squared of theta over cosine of theta times, so the reciprocal of sine of theta is 1 over sine of theta. And so now we can cancel some stuff out. So here in the numerator, we have sine squared of theta, so that's sine times sine, and then in the denominator we have just a single sine. And so when you multiply these two things together, basically the squared is going to go away. It's kind of like if you had like an x squared and an x, it's the same idea. So we're left with, and this is going to cancel out. And so what are we left with? We're left with just sine of theta over cosine of theta is equal to tangent of theta, right? Sine of theta over cosine is the same as tangent. So kind of like, I find these actually kind of like fun or like satisfying, right? Because you don't really know what you're going to end up with. And so it's very satisfying when it actually works out and it ends up with something that is like way simpler than what you started with. So again, as I mentioned at the beginning, you could definitely also do this by splitting it into two fractions. And I would encourage you to try that method and see if that, worked better in this case or worked worse in your opinion. Okay, so we're going to do a couple more examples along these same lines. So let's do, oops, I wanted to switch colors here. Let's do, debating which one to do next. Okay, let's do this one. So this one is going to be tangent of theta. So simplify. Tangent of theta plus cosine of theta over 1 plus sine of theta. So again, we're going to start by putting things in terms of sine and cosine, and then we will make a common denominator. So we know that tangent can be written as sine over cosine. So let me just rewrite our original question here. We know that we can rewrite tangent as sine of theta over cosine of theta. Okay. So in this case, how are we going to get a common denominator? And again, that might seem like a very counterintuitive thing to do here, but it will actually lead us to eventually a simpler answer. So how are we going to get a common denominator? Well, in this case, we kind of just have to force it. So we basically have to multiply the second fraction by cosine over cosine, and the first fraction by 1 plus sine over 1 plus sine. So let me rewrite this with a little more space here. So I can write that multiplication, and then here we'll have, okay, so we're going to go in and we're going to create this common denominator, and the way we're going to do it is we're going to multiply this one by 1 plus sine of theta over 1 plus sine of theta. And then we're going to multiply this one by cosine of theta over cosine of theta. So again, it's definitely going to at least momentarily make this look more complicated, but eventually if we just kind of follow it through, we'll get to a simpler answer. So what happens when we multiply these two numerators together? Well, let's distribute the sign, right? Because we're actually, let me write out one additional step. So let's start by just writing it like this. So sine of theta times 1 plus sine of theta, and then we can distribute it on the next step, over cosine of theta times 1 plus sine of theta. And then here we have cosine squared of theta over cosine of theta times 1 plus sine of theta. All right, so now that these have the same denominator, we can put them together. So I'm going to put them on the common denominator, and in the same step, I'm going to distribute this. So we're going to get sine of theta plus sine squared of theta, and then we have plus cosine squared of theta coming from the other fraction, and then that's all going to be divided by cosine of theta times 1 plus sine of theta. So notice I'm not distributing the denominator, and the reason for that, I mean, partially maybe I kind of know where this is going, and that's why, but so I guess it's for me, it's more about why did I choose to distribute in the numerator? So why did I choose to distribute in the numerator? Well, I noticed that we're adding it to a cosine squared of theta, and that if you distribute, you'll get a sine squared of theta. And we know that sine squared plus cosine squared is equal to 1. And so I figured, if we distribute this sign, then that will help us kind of see maybe how we can combine our cosine and our sine squared. Whereas in the denominator, you're not really going to get anything special or different by distributing this. So I just chose to leave it undistributed, and that will actually, I think, make it easier to simplify in our last step. Okay, so from here, where do we want to go? Well, like I just said, we have a Pythagorean identity, right? We know that by the Pythagorean identity, we know that sine squared of theta plus cosine squared of theta is equal to 1. And so you should really be looking out for getting that, because that's really a way to really simplify your function a lot, right? So this whole thing is just going to become now sine of theta plus 1. And so in the denominator, we're left with cosine of theta times 1 plus sine of theta. So maybe now you see why I said that not distributing it makes it easier to see what you can cancel out here, because here in the numerator, we have sine of theta plus 1. And then in the denominator, we also have a factor of sine of theta plus 1. And so those cancel out. Just be careful with canceling. So I'll try to kind of point out places where I think you might go wrong. But the main thing to remember is that you can only cancel something out if it's a common factor of the numerator and the denominator. So it's basically recognizing the difference between something like this. So if you have like a times b over b, b is a common factor. Or maybe to make it look more like the one we have here, if you have like b over a times b. So because b is a factor of the denominator, and then it's also the whole numerator, you're allowed to cancel it out. But if you have, let's say, b over a plus b, well, this b no longer can be canceled out because it's not a common factor. Like, canceling is basically relying on the fact that multiplication and division are opposites of each other. And here you have division and then you have addition, and they don't cancel each other out the same way that here you have multiplication and division, and those two things cancel each other out. So just be careful. And yeah, I'll try to point out some places where I think you could easily go wrong if they come up in this video. So you're left with 1 over cosine of theta, which is secant of theta. So again, I think pretty unpredictable where that was going to go if you look at what we started with. And it definitely got more complicated looking in the middle, but at the end of the day, it ended up a lot simpler than what we started with. Okay, so we have 2 more that are kind of along this same line. So let's try this one. So we're going to simplify 1 plus cosecant of x divided by 1 plus sine of x. So I want to point out that this is not one where you could use really the like splitting it up. I mean, you kind of could, but because the denominator has 2 terms in it, you can't split those up. It's only the numerator that can be split up. And the reason for that is if you think about how does it work when you add together fractions, the denominator stays the same and the numerator gets added, right? If you add like 1/4 plus 3/4, you don't get 4/8, you get 4/4. So for the same reason, if you're trying to split something up, the denominator doesn't get split up, it's just the numerator that can get split up. So you could rewrite this as like 1 over 1 plus sine of x and cosecant over 1 plus sine of x, but that's not really going to make anything simpler. So instead what we want to do is basically same idea that we've been doing on the other one. So we're going to make a common denominator, or make a few common denominators. Actually, sorry, I lied. We're going to make 1 common denominator. Because, so in the denominator of this original fraction, there's no way, you can't really rewrite anything any other way, right? Sine of x is just sine of x. There's no way to rewrite that as a fraction. Whereas with cosecant, that can be written as 1 over sine of x. So we have 1 plus 1 over sine of x divided by 1 plus sine of x. So now we want to make a common denominator in the numerator. So in this case, it's pretty similar actually to, let's see. Hopefully it doesn't make you too dizzy when I scroll like this. It's pretty similar to this example where you kind of have to force there to be, it's like one of them's a fraction, one of them isn't, but we're going to kind of force them to both be fractions so that we can put them together. So we're going to multiply this 1 by sine of x over sine of x. And I'll just give us a little more space here. So we're going to multiply this by sine of x over sine of x. And kind of force there to be a fraction there. So what do we get when we do that? We get sine of x over sine of x plus 1 over sine of x over 1 plus sine of x. So kind of a confusing looking expression, a lot of the same numbers and things being repeated. So let's combine the fractions in the numerator. So we end up with sine of x plus 1 divided by sine of x divided by 1 plus sine of x. So what is good to observe here is that the numerator here is the same as our denominator. And so that means that if we rewrite our division as multiplying by the reciprocal, so if we rewrite this as sine of x plus 1 over sine of x times 1 over 1 plus sine of x, so just rewriting that division as multiplication by the reciprocal, well then these two are going to cancel out because 1 is in the numerator, 1's in the denominator, and so if you were to multiply them together, you would have a common factor in the numerator and denominator. So then if you multiply these two together, you're left with, maybe let me go to the next line so this doesn't go off the page. So you're left with 1 over sine of x, which is cosecant of x. So I should have said this sooner, but and we only have one more to do together, but hopefully you got the idea that, you know, if you feel comfortable with this, that you should pause the video and try these yourself before watching me do it. Maybe I did say that, I'm not sure. I just made a video right before this for my other class, so it's all blurring together. Okay, so we're going to do one more example along these lines. So in this example, we're going to simplify 1 over 1 minus cosine of t plus 1 over 1 plus cosine of t. So in this case, there's really not much we can do other than make a common denominator from the get-go, right? There's nothing to rewrite. That's really the only thing we can possibly do to kind of put this stuff together. So we're going to make a common denominator, and like a lot of the other examples here, the denominators here don't have anything in common to begin with, so we have to kind of force the common denominator, and basically we're just going to multiply this one by 1 plus cosine of t over 1 plus cosine of t, and then the other one will multiply by 1 minus cosine of t over 1 minus cosine of t. So here we get okay. So let's actually pause it as an aside and talk about what we're going to get in the denominator. So this is like a slight side note, but when you have things that look like this and this, and you multiply them together, it's what's called a difference of squares, right? So a difference of squares is basically when you have anything of the form a plus b times a minus b. And here when I say a plus b and a minus b, like a and b could be like x and 5, or they could be 1 and cosine of t. Like here I'm using a and b to represent really any kind of algebraic expression. So if you're multiplying two things together where the only difference is that one of them is plus and one of them is minus, when you multiply them together, the middle terms are going to cancel out. So if you were to multiply these together, you'd get a squared plus ab minus ab minus b squared. And so you're left with a squared minus b squared. So it's really nice to be able to just recognize these when you see them so that you don't have to multiply everything out. So in this case, if you're multiplying together 1 minus cosine of t times 1 plus cosine of t, rather than multiplying all that out and getting kind of a complicated looking expression, just realize, okay, this is a difference of squares. And so if it's a difference of squares, that means that all I'm going to get is 1 times 1, which is 1. And then I'm going to get cosine of t times cosine of t, and so that's cosine squared of t. So that's going to be our new denominator, right? If we're multiplying these two together to get our denominator, now we know what that denominator is going to be. So I'm going to rewrite these as, so the first one was, the numerator is going to be 1 plus cosine of t. And then the denominator is going to be what we just figured out, so 1 minus cosine squared of t. And then the other part has a numerator of 1 minus cosine of t, and the denominator again is what we just found. Okay, so if we add these two things together, we're going to get 1 plus 1. And yeah, let me kind of group them this way. So we have 1 plus 1 plus cosine of t minus cosine of t, all divided by 1 minus cosine squared of t. So the cosines are going to cancel out, right? We have a plus and we have a minus, and so we're just left with 2. And then the denominator, well, this is another Pythagorean identity, right? So we already have seen ones like this. So Pythagorean identity tells us that because cosine squared plus sine squared is equal to 1, 1 minus cosine squared of t is equal to sine squared of t. And so we can rewrite this as 2 over sine squared of t. And so what's another way of writing that? Well, sine squared of t is equal to, sorry, 1 over sine of t would be cosecant. So 1 over sine squared would be cosecant squared, and then we're multiplying that by 2. So this is 2 times cosecant squared of t. All right. So I want to add one other type of identity to our list, and then we'll do just a couple of examples with that identity. So the third type of identity I want to talk about are what are called, and I want a different color, this color. So the even and odd identities. So these are ones that we've already talked about throughout the course, but we can kind of expand on them a little bit more. So the ones that we know already, we know that sine is an odd function. And so that means that if you're taking sine of the negative of an angle, that's going to be the opposite of taking sine of the angle. Whereas cosine is an even function. So that means that you get the same result whether you do negative theta or positive theta. And we also saw that tangent is an odd function. Okay, so there's 3 more trig functions, right? The reciprocal ones. And so basically the reciprocal ones follow the same pattern as the ordinary trig functions. So because sine is odd, cosecant is also odd. Because it's 1 over, right? If it's like 1 over sine, well, that negative sign is going to come along for the ride, right? Like you're still going to have a negative sign if it's 1 over sine. And so same thing, so the reciprocal of cosine is secant, and so secant is also an even function. And then the last one, cotangent, is also going to be an odd function, just like tangent. Or sorry, I forgot the negative sign. So basically, we can use these even and odd identities to, if we have an expression that involves like negative theta or negative x or negative t, whatever, we can rewrite it as, using the even and odd identities to get our input to be just a regular variable instead of negative variable. So using even and odd identities to simplify. So we're just going to do two quick examples here. So this one is especially quick, but so let's say that we had sine of negative x over cosine of x. So the thing that I want to point out here is that all of the identities we have, so going back to this first page, all of these identities, the ones in blue and green, those ones are only true if the input variable is the same everywhere. So notice it's like theta, theta, theta. It's important that in these identities, whatever angle you're talking about, it's the same angle for every single appearance within that identity. And so, for example, we know that tangent of theta is sine of theta over cosine of theta, but if we have what we have here, sine of negative x over cosine of x, we can't just say, oh, that's tangent of x. We need to first rewrite this so that they have the same input, because it's only when they have the same input that we can really make use of the identities that we know. So in this case, we can use the fact that sine is odd. So we know that sine of negative x is going to be the same thing as negative sine of x. And so now that we've translated it, so now that the inputs match, now we can make use of the identities we know. So we know that sine of x over cosine of x is tangent, so we know that our result is negative tangent of x. And it might seem like we didn't really do much, but it's a really important distinction to understand that, like, it's really not until you have the exact same input in both of the functions that it makes sense to do this simplification that we did here. All right, last example of the video. So let's simplify this one. So we're going to have cosine of negative x times cosine of x minus sine of negative x times sine of x. So just like in the last one, you really cannot combine these until they have the same input. So it would not be correct to say, oh, this is cosine squared of negative x or something like that. And actually in this case it would, but you can't just jump to that conclusion, or that it's cosine squared of x. You need to first translate everything to have the same input, because otherwise it's not being squared, right? Like when you have something squared, that means you have the same thing multiplied with itself. And so when the inputs are different, it's not the same thing being multiplied with itself. And so we want to start by rewriting this using the even and odd identities. So we're going to replace any time where we see cosine of negative x, we're going to replace it with cosine of x. So we have cosine of x times cosine of x. So the first appearance of cosine of negative x, we fix that. And then when we see sine of negative x, because sine is odd, we can rewrite it as negative sine of x. And then we still have this sine of x. And I should put a parenthesis somewhere. I'll put it here. So these two negative signs can combine, and we can now rewrite stuff as being squared. So cosine squared of x plus sine squared of x. And now we can see that this is our Pythagorean identity and that this is going to be equal to 1. All right, so that is it for today. There is a worksheet with a bunch of more examples similar to the ones that we've been doing today. And yeah, I will see you all next time.